Hello everyone from Math 1340, Statistics. It's Professor Winston here again with a video on your KnewtonAlta homework, section 4.2. It's the mean or expected value. Right, those are the two things meaning the same thing, finding the mean or expected value, and separately the standard deviation of a discrete random variable. Right, we're in that chapter 4 right now. Section 4.1, you were introduced to discrete random variables. This is on finding the mean value or expected value of a discrete random variable, and then also the standard deviation, right, a measure of spread of the values of the standard of a discrete random variable. Right. So getting into again, here's a preview of the section. You got the three objectives this time. Now, it's starting me off with find the standard deviation of a discrete random variable from its probability density function. In order to do this, I'm going to have to find the mean. So I will also, when I go into instruction here and show you how to do some problems, I'm going to first show you how to find the mean value or the expected value. Same thing, mean and expected value are interchangeable. So first I'm going to show you how to find the mean of a discrete random variable from its probability density function, and then we're going to go into finding the standard deviation. And then I'll show you also, of course, I'll basically be doing all three of these pretty much back to back close together. Because the last part here is find the mean and standard deviation using a calculator. So I'll show you that as well in the same examples. Alright, so let's get into more instruction here for the standard deviation of a discrete random variable. Alright, and I'll also just read to you the mean one. Alright. So like data, probability distributions also have standard deviations, right? A measure of spread. So how to find the standard deviation? Now the standard deviation for a probability distribution or a random variable is notated with this Greek letter sigma. This is the lowercase sigma. It looks like a tiny 6. See where my cursor is? You've seen this before, right? This sigma was representing the standard deviation of a population before. Now it's it's also representative of the standard deviation of a probability distribution. So you find each deviation between the data values and the mean, which I'll show you how to calculate. Square them, right? So just like standard deviation before, right? You found the mean of a set of data. You then subtracted the mean from every data value. That was the deviations. Then you squared those, right? But now there's this little extra step here when it comes to probability distributions. After squaring the deviations, you're going to multiply these squares by the corresponding probability. All right. Then add these products up, and that'll give you the variance. Right? Remember, variance was sigma squared. And then take the square root, right, for sigma itself for standard deviation. All right. So for example, all right, now I'm going to go here. Let's find the mean first. I'll write out this probability density function on paper and show you first how to find what's called the expected value or the mean value of the random variable. All right. Okay, so here is a probability density function, or abbreviated just PDF, for some random variable called capital X. Right, that's what this chart represents. So down the X, again, if you remember section 4.1, it's all the same. This little x column represents all possible values of capital X here. And down the second column, you have the probabilities of each value occurring. Right? The probability that capital X is 0 has a value of 0 is 20%, 0.2. The probability that X is going to take on the value of 1 is 50%, or a half, 0.5. And the probability that X takes on the value of 2 is 30%, right, 0.3. And all the probabilities are from 0 to 1. And the sum of all the probabilities, right? Remember this, you've seen this before too, right? This, when you see this capital sigma, this E looking thing, this means the sum of, right? The sum of the probabilities should be equal to 1. And you're seeing that here. 0.2 plus 0.5 is 0.7 plus 0.3 would be equal to 1, right? So the sum of all these probabilities, the sum of the values in this column is 1. Great. So this is a valid probability density function. Now, first, in order to find a measure of spread, the standard deviation, I need to know the measure of the center. I need to know what's our middle value, what's the mean. So let's say I want to find the mean value. Oops. Sorry, can't spell. MEAN. Find the mean value of x. Now, another way to put this, another word for this is the expected value of x. And I'll explain much more about what the expected value means when we get to that objective in the assignment. All right, but for right now, let's just talk about how to calculate it. All right, this mean value or expected value of x. Okay, so mean value and expected value are interchangeable. All right. Now, the mean value of x is sometimes just symbolized as, remember this? This probably looks familiar. This is now I know it looks like a U, but this is that Greek letter mu, and it represented before when we just had sets of data. Remember, this represented the population mean. All right, so now when we have probability density functions, we're taking into account all possible outcomes. So it's like a population, right? All possible outcomes, everything. So that's why the mean value of a random variable is labeled mu. And very often, you'll also see a subscript to tell you what random variable we're talking about. So this mu sub x means the mean value of x, or the expected value of x. Another way this is notated in some texts, I don't believe it's notated this way in KnewtonAlta, but you may also see this capital E and then in a bracket the name of the variable. Right, this is also used in some books, just in case you're looking up stuff online. And you see this notation, E of x, like this. This is, again, the expected value or mean value of the random variable x. Expected value. Right, and this is as I said earlier, this is a measure of center. Right? You've seen that before. This is one of those measures of center of the data of our random variable values. This is a measure of center. All right, so how is this mean value calculated? So here's how it's calculated. All right, so I'll just cover this up. So the mean value of some random variable x, mu sub x here, you're going to be adding stuff. All right, so got this summation notation. Here's a formula for it. Now you don't have to memorize this formula, but it'd be nice to know how it's calculated. And then what I do is I'm adding up the following. You're going to take every value of x and multiply it by its corresponding probability. All right, and this is all in parentheses here. So you take every single value of x and multiply it by its corresponding probability, and then add those up, and that's it. All right. So in this example up here, this probability distribution function or probability density function I have up here, I'm going to take, here are the values, here are their corresponding probabilities. I'm going to make another column where I multiply these, right? Where I take every value of the random variable x and multiply it by its corresponding probability. All right, so this first one is just 0 times 0.2. So that's just 0. The next one, 1 times 0.5, is just 0.5. And then the next one, 2 times 0.3, would be 0.6, right? And so for this particular example, where I'm adding these up, so it's 0 plus 0.5 plus 0.6. Right? So I'm getting a total here of 1.1. All right, this is the expected value of x, or the mean value of x, a measure of center. Now, very often this is also referred to as the long run average, right? That's what a mean value is. And like I said, we'll talk more about the meaning of this number when I actually get to that objective in the assignment. Okay, so now that I have this, the next thing I'm going to do is find the Now we're asked to calculate the standard deviation of the random variable x, right? A measure of spread. So for the standard deviation of this random variable, right, of the values of x, and the symbolism here is that sigma, looks like a little 6, but this is lowercase sigma. And again, sometimes, very often, you'll see it as a subscript sigma of x. What's the standard deviation of the random variable x? All right. So again, another crazy formula here, and I'm going to go through it one step at a time with you in this chart and maybe another example afterwards. So it's a big square root, right? You take a big square root, just like standard deviation of a set of data, right? There was a big square root on that as well. And inside here, we're going to be taking a sum. Right, so a big sum, big summation notation. The sum of what, though? All right, what am I adding? So what you're going to do is, another set of parentheses here. I'm going to take every single value of x. I'm going to take every single value of x and find its deviations from the center. How far away from the center value, this mean value, is each value of x. So I'm going to take every value of x and subtract mu. I'm going to subtract the mean value. So these are the deviations. Then square those deviations. So x minus mu, that quantity squared. And then, just like with the expected value, just like with the mean, I take each of these values, each of these squares of the deviations, and multiply by the corresponding probability, the probability that the variable equals that value, that little value of x. All right, we're going to add up these products and then take the square root, right, to get the standard deviation of a discrete random variable. All right, so I'm going to make this chart again, and I'll be right back. All right, so I've created the chart again, right? Just those the PDF, the probability density function. We know that the mean value of x from earlier is 1.1. All right, so I'm going to make one column where we take the deviations and square them. So x minus mu here again is 1.1. So I'm going to take the deviations and square them. All right. So the first one is 0. Right? 0 minus 1.1. That'd be negative 1.1, but then squared. Right? These should all be non-negative numbers as you're squaring them. Negative 1.1 squared is 1.21. 1.21. Okay, then I do the same thing with the next one. 1 for x. 1 minus 1.1 would be negative 0.1. Right, or 1/10. Squared would be 1/100th. 0.01. Okay. Then finally, 2, put in 2 for x. The deviation, 2 minus 1.1, is 0.9, or 9/10. Squared, though, would be 81 hundredths, or 0.81. All right, so here's the squares of the deviations from the mean. All right, all these values minus the mean, minus the expected value, 1.1, then squared. All right, and then I'm going to take all these squares of the deviations and multiply by the corresponding probability. So now we're multiplying the values in these two columns. So I take all these squares of the deviations, so the x minus 1.1 squared values, and I'm going to multiply these values by the corresponding probabilities, right, by the probability column values. All right. So 0.2, all right, all right, so 2 times 121 is 242, but this is 2/10, and this would be 121 hundredths, so we'd have 242 thousandths. So that's 0.242. Right, when I multiply these values, multiply that square of the deviation times the probability. Same here. Now 1 times 5 is just 5, and it's tenths, hundredths, 5 thousandths, right? 0.005. When I multiply those. Then 3 times 81 is 243, and again it's tenths, hundredths, so it'd be thousandths when I multiply them. 0.243. Right. Then, I know this is a lot, and like I said, I'm going to show you the calculator in a minute here. What I have under this square root for the calculation of the standard deviation is the sum of these products. So the sum of these, deviations squared times the probability is equal to what? So adding these up, I got 0 there, and carry a 1, 5, 9, and then 4, right? So 0.490, and this is the variance, right? This is actually sigma squared, right? I haven't taken the square root yet. This is the variance of the random variable x. And so then finally, I take the square root of this number. So sigma is equal to the square root of this sum, 0.490, right, which I'll approximate here. So I'll pull a calculator up. Got my 84 plus, right? 83, 84 are pretty similar. Square root of 0.490, but there's no need to add that. Oh, this is 0.7. Silly me, that's 49 hundredths. I didn't need a calculator for that. This is actually just equal to, not approximately equal to, 0.7. Right. Okay, so there's the standard deviation. And remember, the standard deviation is a measure of spread. Okay. And the larger the standard deviation, right, the further spread out the random variable values are. Right? The smaller the standard deviation, the more tightly packed they are. Another thing we're going to see too is that you could also graph. Now this isn't something they're going over in the KnewtonAlta homework, but we could also make a graph for something like this, where down here I have values of x on the horizontal axis, and then the probability on the vertical axis, probabilities, and just mark off, say here's the number 0, here's 1, here's 2, and those are the only possible values of x mentioned. And then up top, again, just making the scale nice and evenly balanced, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7. And so on. I might as well just label them all, 0.5, 0.6, and then we can make a little, like a histogram. You can make a histogram for a probability density function, just having these values in the middle of a bar. So like what the height being the probability, the height of the first bar, the probability of the x equals 0 is 0.2. So 0.2, and then again I just set it up so that 0's in the middle of the bar. And then the probability that x equals 1 is 0.5. I just set up this bar here so that the height of the bar, and now this is a terrible drawing already because the bar should be the same width. If you recall from making a histogram, this one looks thinner than that one, so this is already a pretty crappy drawing. I apologize. And then the probability of x being 2 is 0.3, so I have a bar with a height of 0.3. And again, I'm trying to make them all look pretty evenly spaced. And here's a histogram for that probability density function for that PDF. Right? And just like for earlier histograms, the larger the standard deviation, the more spread the data will look. The more spread out the bars will be and stuff. They won't be as high in certain places. The smaller the standard deviation, the smaller the spread. It'll be all the bars will be more packed into one area. There'll be less spread and it'll be a bigger peak. Okay. So if you remember all that stuff about spread and the shape of a histogram from earlier chapters, chapter 2, that will help when talking about the standard deviation of a probability density function. All right, and look at this. Right, here's what we said the mean. Remember that mu was 1.1. Right, here's 1.1 on the horizontal axis. Right, here's where the mean is. Right. You see how this is kind of where the in the peak, the center of this histogram here. Right. So. And it would make sense that it would be a little bit to the right of 1, right? Because look, it's not perfectly symmetrical, right? This has a height of 0.2. This has a height of 0.3. So the bar to the right of the middle bar is higher than the bar to the left, meaning it has more weight. So the mean is going to be pulled that way, right? So instead of being directly at 1, it's pulled a little bit to the right, because that bar on the right side is a little bit heavier, right? A little taller than the bar on the left. Again, all similar stuff to Chapter 2 talk about histograms and means and standard deviations. All right, now all that was well and good. I mean, you saw the calculation of the standard deviation, but you see how annoying this could get? Especially, there were only 3 rows here. What if there were 10 rows, 12 rows, 100 rows? Doing this by hand like I just did would be very annoying. All right, it would be almost unwieldy. So let me show you how to enter this into your calculator right now and get the mean and standard deviation. All right, so I'm going back to the original chart. All right, back to the original PDF, which was these 2 columns here, right? The values and the probabilities. And I'm going to enter these columns in my calculator. All right, so remember how to enter columns. You have stat, edit, and then down the first column, say L1, I'll enter the values of x, right? The possible outcomes. So 0, 1, 2. And then in the second column, the corresponding probabilities, or you can almost think of these as the weights, how heavy are each of these values. And you see that 1 is heavier than 2, and 2 is heavier than 0, right? So 1's going to count more when you go to calculate the mean. 2 is going to count a little less. 0 is going to count, a little less than that. But in the next column, L2, I'm putting the probabilities. 0.2 for the probability that x equals 0, 0.5, and 0.3. All right. And I'm going to get out of here, right? Quit. And we're going to calculate. Go stat, hit the stat button again, go over to calculate. Now notice, yes, there are 2 columns. I get it. There are 2 columns, but there's only 1 variable. Right? There's only one random variable here, the values of x. Probabilities are not a variable. Only the variable x is. So I'm going to go to, again, yes, there are two columns, but there's only one variable. So I'm going to click on one variable stats, one var stats. Then the list is the list of outcomes, the actual variable, right? So that was list L1 with the 0, 1, and 2. Then this frequency list, right? You've seen this before, but now the frequency list is the list of probabilities, right? How much is each one being counted? What's the weight of each value of x? So I go second 2, put list 2 there. That was the probabilities, and then calculate. And look at this. Now, I know it doesn't say mu. It says x bar, but remember x bar represented the mean of a sample. Well, it's the mean of a population here this time. It's the mean of the distribution, the mean value of x, the expected value. Remember I said that was 1.1 earlier? Right? I did this by hand. Right? That was this value here on top of this page. 1.1. And look at the top value on the calculator. X bar equals 1.1. So the very top value is mu, is your mean, your expected value of the variable. And then you scroll down a little, not even scroll down, just look further down, and you see sigma. It's right below S, sigma x. That's the standard deviation of the random variable, which was, hey, look, 0.7. Back at this page, exactly what I got earlier, right? See, 0.7 on the calculator for sigma x. Right here, 0.7. So very easy and quick to do this on your calculator, just entering the values of the variable down one list, their corresponding probabilities down a second list, and then go stat, calc, one variable stats, and enter your list and your frequency list, or in this case probability list, and then calculate. And you get the mean at the top and the standard deviation just 4 lines down. Okay? Alright, so now back to the assignment. I know there's a lot of explanation ahead of time, and they go through the same process here, doing exactly what I did, and they got the same stuff, right? The standard deviation is 0.7. Cool. Again, read the definitions. We know what standard deviation is, right? A number that measures how far data values are or probability distributions are from their mean, right? Denoted by sigma. We've talked about discrete random variable in section 4.1. Probability distributions in section 4.1 as well. Alright, so let's get to our problem. Where again, I'll do this one more time by hand, and then I'll just, from here on out, probably just go to the calculator. Right? So here, the table below represents the probability density function for a random variable x. Find the standard deviation of x, right, of the random variable. So notice the values here are 0, 1, and 8 for the possible outcomes, the possible values of x. So again, I'm going to write this down. I'm going to do it by hand, and I'll even make a little graph for you. And we'll calculate the mean, the expected value, the mean of x, and also the standard deviation of x. Okay, so here we are. This is the probability density function for some random variable called capital X. Given the possible outcomes, possible values of x, 0, 1, and 8, and the probability that the random variable x will take on these values: 1/5, which is the same as 0.2, 2/5, which is the same as 0.4, and 2/5 or 0.4 for the probability that x equals 8. All right, so first I want to find the mean, right? If you're asked to find the standard deviation, well, that means what's the standard deviation? Deviation is deviation from the mean, so I need to know the mean as well. All right, so let's find the expected value, or the mean, which is that mu, or mu sub x, because again the variable is called x. And remember what I did. You just take I'm going to make a new column here. You just take every single value, possible value of x, multiply it by its corresponding probability. So 0 times 0.2 is 0. 1 times 0.4 is 0.4. 8 times 0.4 is 3.2. And then you just add these up. 0 plus, 0.4 plus 3.2, 3.6. 3.6. Right. So there's the expected value of x, or the mean of x. Right. Then I might pull a calculator up for this and make another column where we take a look at, now I'm doing the deviations. Take every single value and subtract the mean. Subtract 3.6 and then square it. Right, so I'm going to square the deviations. All right, so I'll pull a calculator up for this. I'm not that good. So the first one, when x is 0, well, 0 minus 3.6 is negative 3.6, and you're going to square that, which will make it positive. All right, so let me go back to so 0. All right, so 3.6. What's 3.6 squared? Basically, negative 3.6 times negative 3.6. I didn't square it. Squared 12.96. Right, so I got 12.96 here. Okay, and then the next one, x equals 1. The deviation from the mean is negative 2.6, and then squared. So just 2.6 squared, and that's 6.76. Right. Then the next one, when x equals 8, what's 8 minus 3.6? What's that deviation from the mean? And that'd be 4.4. Right, 4.4, and then squared. Right, so the deviation is 4.4. Squared is 19.36. Right. All right, and then what we're doing to find the variance, and then we'll take the square root for the standard deviation. We're going to take each of these values, all these deviations squared, and multiply by the corresponding probability. So I'm multiplying these two values, multiplying these two values, and multiplying these two values, and adding them up, and then we're going to take the square root of all that. So I'm going to put all that in one calculation, right? And we'll maybe round it. They're round. It looks like in my assignment, it looks like they're rounding to the nearest hundredth, right? 2 decimal places. All right. So on the calculator, I'm going to put a big square root, and then just make sure all of this is under the square root. So I take the squares of the deviations multiplied by the corresponding probabilities, and then add them up. Right. So we have a 12.96 times the corresponding probability 0.2. Plus, and again, notice this is all underneath the square root. Then the next square of the deviation is 6.76 times the corresponding probability, 0.4, or just 0.4. Plus, and again, still notice all underneath the square root. And then the last square deviation, 19.36, times its corresponding probability, 0.4 again, and that's all under the square root. And we're getting approximately, if I round to the nearest hundredth, 3.61. Right, rounding to the nearest hundredth. Again, this is what was being asked for, this standard deviation. Now I'm also going to graph this for you. Right? I know that's not what's being asked, but I'll show you how to how I would graph a histogram of this particular probability density function. So same deal, right? I got 2 axes. The horizontal axis being the values of the variable, the values of x, and then I'll just put probability of x up here. Right? Probabilities going up. Let's say this is 0.1, 0.2, 0.3, and 0.4. Right? And again, that's the highest any of these is going to get. Let's say there's a value of 0 here, and then 1, 2, It goes out to 8. Right, trying my best to keep things evenly spaced. All right, and the probability that x equals 0 is 0.2. Right, so I make a bar like that, so that 0 is in the middle here. All right, so like this. The probability that x equals 1 is 0.4. Again, trying to keep the bars evenly, just as wide. And the probability that x equals 2, 3, 4, 5, 6, and 7 is all 0. Right? So technically I can make bars of height 0 here, all on the axis. And then the probability that x equals 8 is also 0.4. Right? So it's got the same looking bar as the 1 bar did. All right, so there's a histogram for this probability density function of x. And I'll also mark off where the mean was, right? Now the mean we saw was 3.6. Now 3.6 is about here, right? There's 3.6, right? So you see how that's like a measure of center, right? Because I mean, clearly values are being weighed over here, values are being weighed over here. And there's more, if it was truly symmetrical, right? If it was a truly symmetrical distribution, the middle would be at 4, right? The average of 0 and 8. But you see how there's more weight over on the left side. See the total of the left side probabilities is 0.6, right? So these have weights adding up to 0.6. This is only 0.4. So if it were perfectly symmetrical, the mean would be at 4. But there's more weight to the left of 4 than there is to the right of 4. So the mean is being pulled to the left of 4, as you see here. It's pulled to 3.6. Right? So again, you could do this on your own if you want for any of these. Make a little histogram, and maybe you can see the symmetry, or you can see why the mean is where it is and stuff like that, and talk about how the spread is affected, or talk about a measure of spread, the standard deviation, 3.61. Now 3.61, that's more than 0.7, right? The last example we saw had a standard deviation of 0.7, and those bars were pretty close together. This is much more spread. This is a larger standard deviation, and you can see that in the picture, hopefully. Okay. All right, but again, all we were asked for was standard deviation 3.61. Right. All right, and if I was going on the calculator, one more time, I'll show you on the calculator too. Yeah, on the calculator. Let's pull this back, right? So again, how do you do this real quick on the calculator? In stat, edit, and then down the first column, I've already got 0, 1. I'll just change the 2 into an 8. And then over here, 1/5 is already 0.2. 2/5 is, I'll just change that to 0.4. Or you could just write 2 divided by 5. It'll change it to 0.4 for you, and then 0.4 again. All right, and now I've got the distribution in my columns. Get out of here, then go stat, calc. Again, there are 2 columns, but only 1 variable. So 1 variable stats. List 1 has the list of outcomes. The frequency list has the list of probabilities. I calculate, and you see the mean was 3.6. That's top value, x bar, 3.6. And the standard deviation was 3.61 to the nearest hundredth, right? That's a sigma. So again, very easily done on your calculator for you. And if you do a couple by hand, right, just to get the hang of doing that, get the feel for it. But after a couple, start going to the calculator just to save yourself a little time. All right, so there's another one with a. Now notice the possible values of x here have changed. All right, so I'm just going to pull up the calculator. Go stat, edit, and the probabilities haven't changed, right? 1/5, 2/5, 2/5. That's still 0.2, 0.4, 0.4. Just the possible values of x have changed from to 4, 6, and 8. So 4, 6 and 8. Now based on that, I'd say the standard deviation would be smaller because there's less spread. Instead of 0 to 1 then to 8, if you drew a histogram too, you'd definitely notice that the bars and all the weight would be closer together. Less spread. Well, let's see. Let's get out of here and again do stat, calc, one variable stats, list 1, list 2, all that. See, the standard deviation went from being 3.61 to 1.5, right, if I round that to the nearest hundredth. So definitely less, right? Less spread. Now the mean is different, of course, right? The values before were 0, 1, and 8. Now they're 4, 6, and 8. So the mean is going to be changed, right? So let's see, the mean is 6.4. And they say round to 2 decimal places. So it's again 1.50. And the X here represented the number of documentaries somebody watched in the last month, 4, 6, or 8, and the probability that they watched that many. But you can read the problem if you wish. But the standard deviation rounded to 2 decimal places would be 1.50. Right, 1.50. Again, pay attention to how they want you to enter the answer. Now here again, they do it by hand. Right, you find the mean, 6.4, subtract the mean from all the values, square those, and then multiply by the corresponding probabilities, and add those up, then take the square root. Right, it's a lot. It's a lot to do by hand. Right, but it can be done. All right. Now here, we've already seen this. Find the mean. Now I do want to get into the instruction here because it does go into more detail as to what the mean or the expected value of a random variable means. Right. So into more instruction. So finding the mean of a discrete random variable. Now I've already shown you how. Now here's what it means. Here's what it tells us. Again, it's a measure of center. But the expected value is often referred to as the long-term average or the mean of a random variable, and is denoted by the Greek letter mu, as I've already shown you. All right, this long-term average. This means that over the long term of doing an experiment over and over again, you would expect this average. You would expect the outcomes to all, if you did an experiment over and over and over again, you'd expect the average of all those outcomes to be close to this mu, right? This mean value. So this long-term average is known as the mean or expected value of the experiment. So for example, you toss a coin and record the result. What is the probability that the result is heads? The expected value is a half here, right? You're probably 1 out of 2. But you might toss a fair coin 10 times and record 9 heads, right? 9 isn't half of 10. That doesn't mean anything, though, right? 10 times isn't a lot. When you say the probability is a half, that means you'd expect if you flip the coin a lot, 1,000 times, 10,000 times, you'd expect the number of heads to be about half and the number of tails to be about half, right? Not exactly. I mean, you expect it to be, but you know it's not going to be exactly half all the time, right? When you flip a coin 10 times, you shouldn't, you expect 5 of them to be heads and 5 of them to be tails, but that doesn't mean that's going to happen, right? So probability does not describe the short-term results of an experiment. It doesn't tell you what's going to happen. It gives you it gives information about what can be expected in the long term after many, many trials. So an example of this is statistician, mathematician Carl Pearson once tossed a fair coin 24,000 times for some reason. All right. Since the expected probability of flipping heads is a half, the expected value of the number of heads should have been 12,000 heads, right? If he flips this coin 24,000 times, and because the probability of flipping a head is a half, you'd expect 12,000 to be heads and 12,000 to be tails. Now again, that doesn't mean that's what's going to happen, but if you do something long enough, it should be pretty close. And that's the law of large numbers. He recorded the results of each toss, obtaining heads 12,012 times which is close to what was expected. So in this experiment, Pearson illustrated what's called the law of large numbers. Now, the law of large numbers states that, as the number of trials increases, right, the more and more you repeat an experiment, the theoretical probability and the actual relative frequency get closer and closer together, right? So that means that the actual experimental values will get closer and closer to what you expect, right, to the theoretical values, like Carl Pearson's coin flips. The more times he flipped the coins, the closer his long-term average got to a half. So in other words, after conducting many trials of an experiment, you would expect this average value. So again, this is important. Right? Expected value just means the more and more and more and more times I do this, the closer the average will get to what I expect. It doesn't mean that's what's going to happen. It just means we're going to get closer to that the more and more times you do something. All right. All right. And I already told you how to calculate expected value, and they go through an example here. I'm not going to do this. All right. So let's just get to a question. So again, very simple. Now here, in a game, participants spin a wheel to win a prize, right? The wheel is split into 10 sections, showing how much money participants can win. 6 wedges show $0, 2 wedges show 100, and 1 wedge shows 300, and 1 wedge shows 800. The table below represents the probability density function for the random variable x, where x is the amount won in a spin. Right, so you can win $0, $100, $300, or $800. And then the probability of getting each of those, right? There were 6 out of 10, 2 out of 10, 1 out of 10, 1 out of 10. It says find the mean value of x. What's the expected winnings? Now, if you just multiply these and add them up. So the first 0 times 3/5 is 0. A fifth times 100 is 20. A tenth of 300 is 30. A tenth of 800 is 80. 20 plus 30 plus 80 is 130. The expected value of x, the expected winnings on a spin, is $130. Now, that doesn't mean you expect to win $130 the next time you spin. That can't happen. You can only win 0, 100, 300, or 800 on a spin. What this means, what this expected value of $130 means, it means that if you were to spin 100 times, 1,000 times, 1,000,000 times, the more and more you spun that wheel, the average of your winnings would get closer and closer to $130. That's what expected value means. That's what the expected value tells us. Right? So say you spun it 100 times, and then the first time you got $100, the second time you got 300, then you got 0, then you got 0, then you got 800, 300, 100, 800, 0, 100, 300. You do that 100 times, you take all the money you won, you add it up, divide by 100, that average should be close to 130. You do it 1,000 times, you take all your winnings, add it up, divided by 1,000, that average should be closer to 130. All right, I'm hoping that's clear the way I'm saying this, but it's 130. Okay, so finding the mean, very, very simple. All right, so I've done the mean now several times. Here you have payout amounts and probabilities, and you're just going to be multiplying each amount. Now, the columns are going horizontal instead of vertical. Right? No big deal. Right? So I'll let you read this, and again, it's just calculating mean. So I'm just going to cheat on this and see they're doing the same, taking each payout amount times the corresponding probabilities and adding them up. This is the exact same kind of problem. All right, again, they're horizontal, the rows instead of columns. But no biggie. You just multiply the payout amounts by the probabilities, and again, read through it, and maybe you can make sense of it. But I'm just going to cheat. I've already shown you how to calculate the mean several times now. Okay. We got one more, and then very similar. All these mean problems seem to be similar. And then we probably have one more, and we probably have two more standard deviation problems. Now I've already told you how, now this one has 4 rows. And you have to find the standard deviation. You saw how long it took with 3. So it'd be even more annoying with 4. So again, I would just simply, I'll pull up the calculator one more time. Show you how. All right. So again, one more time. Stat, edit. I'm going to enter, the possible outcomes in list 1 here. So 0, 3, 4, and 8. And their corresponding probabilities in the next column. Now I'll just enter fractions, 1/6, because 1/6 is like 0.1666666. I'm not going to round that. I'll put 1/6, then 1/6, 1 divided by 6, 1 divided by 3, and 1 divided by 3, right? 1/3. Okay, and then get out of here, go stat, calc, 1 variable stats, the list of outcomes, the probability list is there, calculate. And you see the mean value, the expected value is 4.5. The standard deviation of the variable would be 2.81 if we're rounding to 2 decimal places, right? So back here, 2.81 strikes, some sort of scorekeeper, bowling league, you can read the problem, but the standard deviation, 2.81. And again, they go through and show you the entire thing by hand. Kind of, again, it's kind of annoying to do by hand, the standard deviation. I would just say use the do it once or twice, get the hang of that, but use the calculator afterwards to save yourself some time. Alright, so I'm just going to cheat on the rest of this because it's all the same. Just pay attention to what they're asking you for. Do they want the standard deviation? Do they want just the mean? How many decimal places? Alright, so I'm just going to cheat on the rest of these. I know you can't do that, I apologize, but you're the one who needs to learn this stuff, practice it. And then the final one is using the calculator, alright? So these are just going to be longer charts. The final objective is calculate the mean and standard deviation for a discrete probability distribution using a calculator. So you see now it's just longer charts. So unfortunately they're going to, it's going to take longer to enter, but you can still do it, alright? So you have your list of possible outcomes here, the probabilities of each, and they want you to find the mean and standard deviation, round to 2 decimal places. Right. So again, I would enter 0 through 9 here down list 1, all these probabilities down list 2, go to stat, calculate 1 variable stats, make sure L1 is your list, L2, whatever list you put it in is your probability list, your frequency list, and then calculate. And you'll be getting these 2 numbers here that show up right now. Eventually, yeah, so 3.57, 1.78, okay. All right. So again, I'll just see if there's any different kinds of problems. I don't think there are. Read through the problem if it's an actual word problem, see what the variable x means, right? Here x represents the number of employers that they thought they would have to take have during their working lives. And yeah, so again, this is just a little annoying. It's a lot of data entering into your calculator, but still doable. Right? Just longer charts. So enter 2 lists, 1 variable stats, calculate, make sure you know what the x bar represents mu, and then that sigma represents the standard deviation. And pay attention to how many decimal places, right? 3 decimal places, notice here, round to the nearest thousandth. Alright, so this one's the same kind of problem. Again, I'm just flipping through this just to see if there are any different kinds of problems for this objective. It doesn't look like there are. Alright, so hopefully you only need to do 4 or 5 of these things for the third objective. And yeah, this is absolutely no different. Alright, so I believe. All right, so that's all the kinds of problems there. Lots of data entry, and that's it. Okay, so you got your mean, and you should be able to calculate these things by hand on a piece of paper. But again, also you can refer back to your calculator and those lists. So you have your mean, right, a measure of center for a particular random variable, the values of a random variable, and you have your standard deviation, again, a measure of spread. And if you want to draw histograms too, totally cool. In fact, in future sections, I'll do them on the calculator again. I'll show you some histograms for probability density functions on your calculator. Okay. All right. So hopefully this video helps you as a nice little guide through section 4.2 when you do it on your own. Obviously, if you have any questions, let me know. And thank you very much for watching.